In this set of slides, we will review correlation and simple linear regression. What is correlation analysis? Correlation analysis is the study of the relationship between variables. Let's take a look at the example below. A health analyst is interested in studying the relationship between time spent in a rehab for patients with cardiac surgeries and their improvement score. Improvement score here indicates how fast they're able to return back to their normal activities. As you can see below, we have two variables. We have number of rehab hours, ranging from 10 to 50, and improvement score. The higher the score, the more rapid the improvement is. If we would like to examine the relationship between the number of rehabilitation hours spent and the improvement score, we need to first identify the type of variables we have in this example. Both of these variables are continuous. Therefore, a good visual tool for plotting data between two continuous variables is a scatter plot. The assumption or claim is that the number of rehabilitation hours is related to the improvement score. Specifically, as the number of rehabilitation hours increases, it appears the improvement score also increases. We refer to the number of rehabilitation hours as the independent variable and improvement score as the dependent variable. So the dependent variable is the variable that is being predicted or estimated. We usually use the letter Y to denote the dependent variable. The independent variable is a variable that provides the basis of estimation. It is the predictor variable. It is a common practice to use a scatter plot or a scatter diagram where the independent variable is placed on the x-axis and the dependent variable is placed on the y-axis. A scatter diagram is a great tool to plot the data between two continuous variables. A scatter diagram, as mentioned earlier, is used to assess the relationship between two continuous variables visually. Therefore, the x, or the independent variable, is placed on the x-axis, and y, the dependent variable, is placed on the vertical axis or the y-axis. Now, there are three ways in which two variables can be related. There might be a positive or direct relationship between two variables, or it can be inverse or negative, or there might be no relationship. The relationship between two variables is measured by the correlation. Correlation is denoted by R. R refers to sample correlation. And overall, the correlation is a measure of the degree or strength of association between two variables. R is also called Pearson's R and Pearson's product moment correlation coefficient. Correlation can assume any values between -1 and 1. If the correlation value is -1, then the correlation between two variables is perfect negative, and it is a strong correlation. In general, negative values indicate an inverse relationship between two variables. If the value of the correlation is 1, then the correlation between two variables is perfect, positive, and it is a strong correlation. In general, positive values indicate a direct relationship between two variables. If the value of the correlation is 0, then there is no correlation, or the correlation is weak. Overall, as the values of the correlation approach 0, the correlation is quite weak. In this slide, we see graphically the three types of associations between two variables. As you can see, when the value of the correlation is below 0, we have a negative correlation, which means that as the values of the independent variable, which is the variable on the x-axis, increase, the values of the y variable decrease. When the values of the correlation are above 0, meaning positive, then as you can see, we have a positive relationship here, which is expressed as a straight line, where as the values of x increase, then the values of the y variable increase as well. Finally, you can see that when the correlation value is 0 or close to 0, there is no association. There is no clear linear pattern between the two variables. How do you create a scatter plot in Stata? Going back to the previous example, where we're interested whether to examine the relationship between the number of rehabilitation hours spent and the improvement score, we can actually create a scatter plot in Stata. So we can use the command graph two-way scatter and then include the variable names as shown in the data file. So the variable name for the improvement score is improve score, and for rehabilitation hours is rehab hours. Or you can simply say two-way scatter and then the variable names as they appear in the data set. Now the dependent variable is improvement score and is placed in the y-axis. So we enter that first in the command line, and then the independent variable rehab hours is placed on the x-axis. So it is placed in the command line after the dependent variable. So as you can see on the right, the scatter plot shows a positive association, which means that as the number of rehab hours increases, the improvement score increases as well. Now let's suppose we would like to run a correlation in Stata and test its statistical significance. So the question is there a significant association between the number of rehab hours spent and the improvement score? To answer this question, you can use the command correlate in Stata and then simply enter the variable names as they appear in the data set. So first you will have improved score, which is the dependent variable, and then rehab hours, which is the independent variable. As you can see below, we have an output that shows the value of the correlation between those two variables, which is 0.8792. So this value actually indicates a strong positive correlation. Now, to really test the significance of this correlation, we use the pairwise correlation command. So this command is pwcore, enter the variable names, comma, SIG, star, and the parenthesis 0.05. This means basically that we consider a significant association at an alpha value of 0.05. So by placing SIG star, we're telling Stata to identify the significant association by placing a star at an alpha value of 0.05. So the interpretation of this then would be that the correlation of 0.8792 is statistically significant since the p-value is 0.0008, which is less than 0.05. This means that as one increases the amount of time spent in rehab after a cardiac surgery, his or her improvement score significantly increases. This shows that increasing the amount of time spent on rehab can play a significant role in improving one's ability to return to daily activities quickly after this type of surgery. Next, we will review the simple linear regression. Regression analysis is the process of constructing a mathematical model or function that can be used to predict or determine one variable by another variable. The most elementary regression model is called simple regression, which involves only two variables. That is the dependent variable y and one dependent variable x. A mathematical form of the regression equation can be written as y equals a plus bx, where y is the average predicted value for any value that the independent variable x assumes, a is the y-intercept, and y equals the intercept when x assumes the value of 0. B is the slope of the line, or the average change in y for each change of 1 unit in x. In statistics, the equation we reviewed earlier is expressed as y equals beta 0 plus beta 1 x plus epsilon. The letters beta and epsilon are Greek and are used to denote parameters. Now, y here is the same as earlier. It is the mean value of the dependent variable when the value of the independent variable assumes certain values. B0 is the estimate of beta 0 and is the y-intercept and is when actually x equals 0, then the mean value of y equals the intercept. B1 is the slope, which indicates the change in the mean of y per 1 unit change in x. Epsilon is estimated by E. E is an error term that describes the effect on y of all factors other than x. Let's look at an example of a simple linear regression model. Let's suppose we're interested in predicting length of stay at a hospital after surgery based on average weekly walk-in time after surgery. So in this case, we have two variables. We have the dependent variable, which is length of stay, and it is shown in the second column of the spreadsheet, and one independent variable, our x here, which is average weekly walking time after surgery. So the above spreadsheet shows the data collected for each patient for average walk-in time and length of stay at hospital in days. As a visual tool, and one of the first tools we use to assess associations between two variables, is a scatter plot. In this case, we would like to assess the association between these two continuous variables to determine what kind of association we have. And as you can see above, you can see that this is a negative relationship. This means that as weekly walk-in time after surgery increases, length of stay decreases. If the scatter plot shows that there is a linear relationship or approximately linear, then you may conduct regression analysis to predict the average length of stay at hospital using average walk-in time in minutes per week as the predictor or independent variable. Another way to state this is to say that you may conduct regression analysis to examine the effects of average walk-in time on length of stay at hospital in days. When you conduct regression analysis, the goal is to estimate the effect of a predictor or independent variable on the dependent. The effect of the independent variable can be estimated via the computation of a regression coefficient. Now, regression coefficient is an estimate of the slope, which is the change in the dependent variable per one unit change in the independent variable. We estimate the regression coefficient associated with the independent variable using the least squares point estimates method. So let's take a look at a graphical presentation of the simple linear regression model. The black dots that you see in this graph indicate the data plotted for these two variables, for x and y. X, your independent variable, and y, your dependent variable. The blue line is the regression equation model that is built based on these data. Now you can see the beta 0 or B0 is your y-intercept, that is the value of y when x equals 0. Now you can also see the slope. The slope, beta 1 or B1, is 1 unit change, is the value of y per 1 unit change in x. Now, the distance between each plotted value, basically your black dot, from the model that was built based on the data is an error term. These are called residuals and error terms. Basically, it is a variation that your model did not account for. The least squares point estimate is a method that we use to compute the regression coefficients, that is, the intercept and the slope of one independent variable or many independent variables. So the estimation prediction equation here will be y hat, which is the estimated value of y, equals beta 0, the estimated value of the intercept, plus beta 1, the slope, the estimated value of the slope associated with the independent variable x. So the least squares point estimate of the slope beta 1, as you can see, can be calculated by the following formulas, which involve the sum of squares of the product x and y over the sum of squares of the x's. That would be the value of the slope associated with the independent variable. The formulas may look complicated, but it is fairly straightforward to actually compute the sum of squares based on one independent variable. Obviously, these can get very complicated once you have more than one independent variable. And then you also have the least squares point estimate of the y-intercept. That will be beta 0, and the estimated value of beta 0 is beta hat 0. And it's fairly easy to compute. Once you find the slope, you can simply do the arithmetic and rearrange the formula, your regression equation formula, and find the value of the intercept. So let's suppose we would like to estimate the average length of stay when the value of x, basically walking time, is 40 minutes per week. So once we compute the regression equation, then we can simply enter the value of 40 into the equation and then find what the value of y would be. Now, to get there, in other words, to obtain the estimated regression equation, you need to compute the values of the intercept and the slope. It's very simple to compute the values of the slope and the intercept when you have a simple linear regression model that involves one independent variable. And as you can see here in this table, you can list the values of y, x, and then simply follow what you're supposed to do based on the formula and compute the values of x squared and the product of x and y. Once you find the intercept, which in this case is 15.84, and the slope, which in this case is negative 0.1279, then you simply enter these two values into the regression equation on the top here, then place 40 minutes for the value of x, and find that the amount of days that one is expected to stay in the hospital for walking 40 minutes a week is 10.7 days. This may seem quite complicated, but again, it's very straightforward. You simply need to calculate the sum of squares, and once you do that and you find the value of the slope, then you can solve for the intercept and find the value of the intercept. One thing to remember here is that once you compute the regression equation and you are seeking to find the values of x, you cannot go beyond the values of the actual data for x. As you can see here, the values of x go from 28 to 62.5. This means that you cannot really try to find what the value of y may be for a value that is outside this range. So for example, you should not use a value of 65 minutes to find what is the average number of days that one may stay at the hospital if that person walks 65 minutes a week, because 65 falls outside the range of the actual values for x. It is very important that we calculate the sum of squared errors. The sum of squared errors is indicated by SSE, and we have seen this before from the ANOVA, analysis of variance. Now, the SSE provides an estimate for the amount of variation that is not explained by the model. So once you have the sum of squared errors, then you can calculate the mean square error, which is a point estimate of the residual variance. So it is S squared equals MSE, and the MSE is simply taking the SSE, the sum of squares, divided by n minus 2. Then you can take the square root of the residual variance and find the residual standard deviation. And going back to the example, you can calculate the residuals by simply taking the predicted value of y and subtracting it from the actual value of y, or all of the values of the dependent variable y as shown in this graph, in this table. And then you can square them, and that will give you the values for the residuals for this particular example. So SSE is found by simply squaring the differences between y and the predicted value of y, and then summing all those differences, square differences. Now, how do we get the predicted value of y? For y is just simply using the regression equation we calculated earlier. And for example, for value of 28, if you take the value of 28 and place it into the regression equation we calculated earlier, then you will find that the predicted value for y is 12.25. So when you take the difference between 12.4 and 12.25, that difference will be 0.1412. And if you square that, it will come out to 0.019937. And you repeat the same process for all of these values, and then you come up with an SSE of 2.568011. So this is your SSE. Once you find the sum of squared errors, then it's very simple to find the S squared. You just simply put it into the formula, and that comes out to be 0.428. A square root of that, which will give you the residual standard deviation, is 0.6542. Computing the unexplained variance, or SSC here, the residuals essentially, is very important because we use this information to test the assumptions of the linear regression model. In this slide, we are testing the significance of the slope. If the regression assumptions hold, we can reject the null hypothesis that beta 1 equals 0 at a level of significance, usually 0.05, even only if the appropriate rejection point condition holds, or equivalently if the corresponding p-value is less than alpha. So when you set up the hypothesis for the slope, the null would say that beta 1 equals 0, while the alternative may be directional, in the sense that the slope could be positive or negative, or you may leave it as a two-tailed test, which means beta 1 does not equal 0. And you could use a rejection region method where you have to identify the critical values, or simply use the p-value. As you can see, as you will see a little later, when we do an example in Stata, we use the p-value method. But essentially, some software use a t-test to test the hypothesis. And when you use the t-test is simply calculated by taking the value of the slope and you divide it by the standard deviation of the slope associated with the slope of that independent variable. One can also test the significance of the y-intercept. If the regression assumptions hold, one can reject the null hypothesis, which states that the intercept equals 0 at a level of significance 0.05, even if the appropriate rejection point condition holds, or equivalently if the corresponding p-value is less than alpha. Again, the alternative hypothesis, just like previously, can be directional in the sense that the intercept can be positive or negative, or simply a two-tailed test. Usually is set as a two-tailed test, and the p-value is used in the hypothesis testing. The simple coefficient of determination, R squared, is simply the explained variation over the entire variation of the model. R squared is essentially the proportion of the total variation in the dependent variable that can be explained by the simple linear regression model. Just as a reminder, we have the total variation, which is the total sum of squares, and we have explained variation, that is the variation that can be accounted by the model, basically by the one independent variable in this case. And we call that the regression sum of squares. And we also have the unexplained variation that we covered a little earlier, and that is the error sum of squares, SSE. Now, let's see how you would run a simple linear regression model in Stata and test the significance of the overall model using the previous example of length of stay. In Stata, you use the command regress to run linear regression. Then you enter the name of the dependent variable, which in this case is length stay or length of stay, and the independent variable walk time. And once you complete the command line, then you will obtain the output shown below. The table in red above is an ANOVA table that provides information about the significance of the overall model. The word model corresponds to the one independent variable in the study, which is average weekly walking time. And you can see its estimated variance along with the residual variance, unexplained variance by the model. So we have the sum of squares for the model, and then we have the sum of squares for the residual. Then the F test is computed, which in this case is 53.69, and the p-value that is computed based on this F test is 0.0003, which is very small and essentially means that the average walk-in time after a surgery significantly predicts length of stay at a hospital. The R-squared value is 0.8995, and this means that the average weekly walk-in time after a surgery explains about 90% of the variation in length of stay at a hospital. We also have the adjusted R-squared, which we will cover it in later lessons. Continuing from the previous example with the regress command, where we ran a simple linear regression model on length of stay using walk-in time as the independent variable, we see here in the green table, highlighted in green, we see the values of the regression coefficients for the slope for walk-in time, which is negative 0.127, and the intercept, which is 15.83. In this table, we can also see the values of the standard errors associated with each of these regression coefficients, along with the t-test, testing for the significance of the slope and the intercept, the p-values, and the confidence intervals for each of the regression coefficients. So this is the table from which you obtain the regression coefficients to put together the regression equation of y equals 15.84 minus 0.1279x. Now remember, from the scatter plot that was constructed earlier, the relationship between walk-in time and length of stay was negative or inverse. And this is reflected here in the value of the regression coefficient, which is a negative one, indicating the negative correlation or association between walk-in time and length of stay. Now let's interpret the slope and the intercept. The interpretation of the slope will be as follows. For every 1 minute increase in average weekly walk-in time, length of stay at a hospital is reduced on average by 0.1279 days. You will say reduced again because the coefficient value of walk-in time has a negative value, indicating a reduction in the dependent variable. Now, for the interpretation of the intercept, you would say, when walk-in time equals 0 minutes, in other words, when one person does not walk at all, then the average length of stay is 15.84 days. A number of times we do not bother interpreting the intercept because the intercept may not actually have a meaning that makes sense for the particular problem. Now that we interpreted the regression coefficients, let's take a look at the significance of these coefficients. So we're back again at the table highlighted in green, and specifically looking at the values of the t-test and the p-value associated with walking time, with basically the regression coefficient for the slope. So the question is, can we conclude that average weekly walking time significantly predicts average length of stay after surgery? Or does average weekly walking time significantly influence average length of stay after surgery? Whichever way you like to ask the question, essentially you're looking to see if walking time is a significant predictor of length of stay. So to answer this question, we look at the value of the t-test and its associated p-value for the slope. Indeed, for the t-test, we have a negative 7.33, and we can compute the t-test by simply taking the regression coefficient of negative 0.1279217 and divided by its standard error of 0.0174573. And that yields a t-test of negative 7.33. So when we look at the p-value for that regression coefficient associated with a t-test of 7.33, we see that the p-value is 0.000, which is a very small number, much smaller than 0.05, which is the level of significance. Thus, we can reject the null hypothesis that average weekly walking time does not predict average length of stay after surgery. So essentially, this means that the particular sample provides sufficient evidence that average weekly walking time significantly predicts average length of stay after surgery, or that the predictor of walking time has a significant effect on length of stay. The assumptions of the regression model are as follows. 1, the relationship between y and x is linear. Using a scatter plot to check this assumption can be fairly straightforward. The dependent variable, y, has to be continuous. And third, which is a very important assumption, is that the residual term or the residuals have to be normally distributed for each fitted value of the independent variable x. And we can check this with a histogram of the residuals, but also statistical tests, specifically testing the hypothesis that the residuals are normally distributed versus not being normally distributed. The spread of the residual terms is also a very important one, and it indicates that the residuals should not spread out more or less when x increases, and we call this the homoscedasticity assumption, and we can check this with a plot of the residual values against the fitted or use statistical tests. We can do both. We can use plots and statistical tests to test these last two assumptions, the normality of the residuals and the homoscedasticity.